The recording is on. Okay. Yeah. Very good evening, friends, and welcome to you all for today's lecture, the fifth one in the structural engineering series, organized by ACCE Institute's working group. In today's time, special and general purpose computer softwares have obliterated hand computations and code referencing. Any newly qualified civil engineer will be concentrating on learning skills to handle the computer software. Nevertheless, a first-hand dealing with analysis and code verifications will help the designer to internalize the principles, theoretical concepts, and the codal provisions. R.C.C. design detailing is also a practical subject where a lot of design specifications are a function of construction and field conditions. It is very essential for a designer to understand them. Keeping this in view, today's lecture, Design of R.C.C. Elements, Footings, Columns, Beams, and Slabs, is an attempt to project the key concerns of design like safety, serviceability, durability, etc., and go through the design process for various components of an R.C.C. frame building like slabs, beams, columns, footings, and staircases. Detailing of reinforcement for all the components are also going to be discussed. Even though it requires an exclusive treatment, the design and detailing of liquid retaining structures will also be briefly discussed. Friends, it's my privilege to introduce today's speaker, Engineer C.N. Yadunandan. Engineer Yadunandan retired as Associate Professor from S.J. College of Engineering, Mysore, after nearly 36 years of his valuable teaching in structural engineering. He guided a large number of students in M.Tech structures, published about 25 papers, and authored 3 books. From the Association of Consulting Civil Engineers India, we are proud to inform you all that one of his books, Structural Steel Design Handbook as per Limit State Method of Design, was published by Association of Consulting Civil Engineers India and released during the Silver Jubilee celebration of ACCE in the year 2010. Engineer Yadunandan is rendering his professional services as a full-time structural engineering consultant after his retirement from teaching in 2012. A number of projects for which he has provided structural designs have been recognized and awarded. Engineer Yadunandan is a technical advisor to Mysore Nirmiti Kendra and also served on several committees of Mysore City Corporation. He is a fellow of the Association of Consulting Civil Engineers India. Engineer Yadunandan has also served as a secretary and chairman of ACCE Mysore Center and was one of the main contributors in ensuring that the center became active and vibrant, which we have all been witnessing over the past few years. I now request Engineer C.N. Yadunandan to share his knowledge with us all today. Yadunandan, just wait, I'll unmute you. Can you unmute yourself now? Yes.
Okay.
Okay. And if you hold on a second, I'll just pass you on to make you a presenter.
Yeah.
Yes, sir. The floor is all yours.
Yes.
Let's start off.
Yes. किस तरह चले? Hello.
Yeah, it's there. You can go ahead.
Yeah, let us start. Yeah. Good evening, everybody. At the outset, I congratulate ACCE for its active role in disseminating professional knowledge and I appreciate its efforts in direction. After a very successful run of the sustainability series, they are into the second one about engineering series, and I'm proud to be a part of this lecture series. My personal thanks are due to Dr. Ajit Sabnis and Engineer Ranganath for their stewardship in arranging this webinar. This talk is on the design of reinforced concrete elements. The target group mentioned being fresh graduates and engineers in the beginning phase of their career as designers. I presume all of them had a basic course in R.C.C design and are introduced to the fundamentals. I have therefore considered summarizing the design approach for the R.C.C components mentioned and orient the designer towards a set of concerns and objectives which ensures good design and good performance. I will try to highlight how the objectives are achieved in design by analysis and practical control measures. The role played by the code of practice in this direction is also discussed. With this, I begin my talk on the design of R.C.C elements, where we start with design. So let me go to the fundamental question of what is design, and then go ahead with the details about the design of various components. As we see, reinforced cement concrete has a history of over 120 years. That means it has just come in the 20th century beginning and over a century old. Over these 120 years, it has seen a phenomenal development, and it is the most widely used construction material today. Over these years, there has been a tremendous change in design understanding also, that it has transformed the very meaning of. So, what is design? Does it mean sizing the structure that it does not fail or collapse under calculated load? The answer said no for this question. But it's still not the same as just sizing the structure for collapse under calculated load. Because we engineers came to realize that loads and material strengths are not deterministic quantities but variables. Therefore, safety or failure is also a probabilistic condition. We therefore have to say that the objective of design is to size the structure so that there is a very low probability of collapse occurring. Further, we cannot base design on hypothetical concepts like stress, but on realistic, measurable, or observable parameters like strain, displacement, crack width, etc. This comment is coming because earlier in the working stress method, we were just fixing up permissible stress based on the strength characteristics observed in the laboratory of the materials, and we are trying to contain the stress, where stress per se is not a quantity which can be seen. Whereas if we say that the collapse of the structure is imminent, where you can observe it at this load, or at this load, the crack width is 0.15 meters, or 0.15 millimeters, sorry, or at this load, the dispersion is 20 millimeters. These are quantities which are measurable, which are observable, and we use these quantities to measure the performance of the structure or fix the performance of the structure, and that way try to control the behavior of the structure. And the design has to take care of so many other performance requirements, such as serviceability, is limiting deflection crack fits during service. Ductility, the failure has to be ductile. It cannot, the structure has to give sufficient warning before failure. Reinforcement being a very vulnerable material for fire, we have to protect the reinforcement and provide fire resistance for the structure. We have to provide durability to the structure because there are so many degradation mechanisms reducing the durability of the structure. We have to see the durability of the structure is such that it performs over its design life satisfactorily. Similarly, water tightness, the structure has to be watertight such that there is no ingress of water and touching the reinforcement and the corrosion or carbonation process doesn't take on. So these conditions of performance are called limit states, and the design has to satisfy those conditions. Thus, in the limit state method, as we see, this is called the limit state method, and in this limit state method, the important changes in approach are the considerations from deterministic to probabilistic conditions and observation of the limit state behavior in terms of real quantities instead of hypothetical quantities. In this slide, therefore, we can define design as the process of fixing the shape, size, and characteristics of the structure to see that there is a low probability of all these limit states being crossed. That way, for the strength limit state, we model a failure situation corresponding to a ductile failure and consider highest expected actions which are scaled up to have a low probability of exceeding the lowest possible resistance. The resistance of the structure is down. So this is a fundamental basic graph for defining the performance structure, where we see we quantify the loads in terms of a normal distribution curve, the red curve. This is the variation of the various values of the loads taken considering as a normal distribution curve. This is the probability of having peak or maximum value which is scaled up by a certain factor. We multiply the load by a certain factor so that we see that how the collapse occurs, it has to be at these magnified loads. So if the resistance has, if the variational graph of normal distribution curve is this, we have to set a normal distribution curve for the resistance in this blue line graph, where you see this is quite more when compared to the load's value. It is higher than that value, and its variation is seen like this. And this value of the resistance is scaled down considering the reliability of the material, whatever strength we are given it, whether it's how reliable it is, how best it is, to acceptable it is. We just take it, like for example, for concrete is a man-made material, the chances of it going below a certain value are quite high, therefore we have to scale it down well, whereas steel, which is produced in the factory, has got a good reliability of quality and strength in production. So we keep the scaling down a little less, not as much as concrete like that. So we take that and we use partial factors of safety and provide a scaling down factor for the strengths. So these scale down strengths have a very low probability, as you can see the overlap region here, which is a 5% region we call of going below the load values, or there's a 5% probability of loads going at the minimum lowest strength values. So this is the basis where we see that the central safety margin, as you can see, the load margin and strength margin are shown there. You can understand, therefore, that this is the undesirable range which should not occur, and we take care to see that this range is not reached in design. So we consider just one factor is probability is fine. Probabilistic approach is an eye-opener. It will tell you this. You have to consider all these variabilities and do it. But statistics can be used to mislead. For example, I can say there are various causes of failure. Farmer failure is 60%. The material failure is 15%. Accident 15%. Foundation 15% failure. Lack of maintenance 10%. Overloads causing 5%. If you take all that, total is 5%. So that our designs never fail. It's only all the other reasons we put together which are making the structure fail. Statistically, you can affect it just in a lighter way. Let's put that slide. But we are considering the probability as a very, very realistic approach to the consideration of design and strengths, and we have developed the theory of design of concrete structures on that basis. So the section is designed, that is the material strengths and quantities are provided to take care of the limit state of collapse and check for the information during service, that is the limit state of serviceability. So this is the basic design procedure. We take care to see that we consider the limit state of collapse, we fix up the dimensions of the structure corresponding to that such that we obtain a ductile failure, and then check it for the deflections, liquids, etc., and various other limit states. Thus, the designer has to have these major concerns for designing. So, this is the important. While you are designing, what is in the background of your mind, what you should provide in the structure. These major concerns, the first one is the strength and ductility. A very realistic model of the failure situation has to be built up so that a ductile behavior is considered, so that there is a sufficient yield range giving warning of an impending failure. In a sense, the design has to be controlled to react to the forces in a specified manner. So this is the basis. We are trying to control the design that the ductility is guaranteed. Ductile failure is going to occur if at all failure is going to occur at overloads. And of course, it is not sufficient that if one section is designed that way, we are trying to see or make a structure in such a way that we build in redundancy to the structure. We build a robust, rigid framing of components so that load effect is resisted by a large number of sections and failure mechanisms which cause the collapse of the structure do not occur. Next concern is the durability. In the structure, it is necessary to protect the materials of the structure from environmental conditions and see that they perform well for the design life. For example, if you take mainly reinforcement, corrosion of reinforcement is a serious concern in R.C.C structures. Water is a strength-giving elixir in green concrete and also in the hardening stages, whereas it is a poison for the concrete during service, as it is the agent of corrosion of rebar and to a certain extent carbonation also. So concrete has to be made dense and watertight to protect the reinforcement, and you have to provide sufficient protection by means of cover and other means to the reinforcement. Apart from this, all these achieved with an economy that we cannot put very large sections, put more reinforcement and see that they are satisfying these conditions. Our objective is to do more with less material. But the very reason for moving from working method to this was that we were not utilizing the strength of these materials to the maximum possible extent because we did not know much about their behavior. We were assuming they were linear, elastic, and trying to contain the so-called stresses by assuming a linear behavior to a certain value. But based on laboratory observations today, it is possible for us to construct a situation of failure where the complete section has resisted the load and the maximum strains have been reached, and corresponding to this maximum strain reaching condition, we are trying to find out the force and stresses corresponding to that condition. The next concern is constructability. That the details of design must be suitable to be constructed as desired. You cannot put a large amount of reinforcement within a small concrete body and ask it to provide the reinforcement where there is no space for concrete, or where it is difficult to place the concrete with the necessary density. And similarly, the placing of concrete also has to be taken care of over the forms and how easy it is to pour, and all these details of the cross section have to be seen correctly, and you have to make the structure constructible. So these factors of concerns are most important when we are going ahead with the design. The object of structural design is to fix the size and section details of the structural components, to make the structure take the specified loads economically and safely over an acceptable time. There is we fix up that the design, the structure lasts a certain lifetime. Depending upon the type of the structure, we fix up from anywhere from 50 to 100 years. And then we have to see that it performs well and steadily over this design life. The design process involves the use of various thumb rules and design constraints to have satisfactory performance. We use mainly to get all that information by the codes, and these are, let us say, control guidelines. This information is provided to the designer by the design codes, which specify all the design data required, the thumb rules required, the control guidelines, etc. Basically, the code is a compendium of all information needed for the analysis and design of various components. Its objective is to assist the designer by providing tabulated standard values for easy computation and practical guidelines. Both countries have their own design codes so that all designs conform to the same standard guidelines over the region. There is a uniformity in design so that one can check the other's design and they have the same approach. In addition to the code, design aids and explanatory handbooks are most often prepared to simplify and reduce repetitive design calculations and office time. Here is a comprehensive list of such IS handbooks. As you are maybe familiar, but during your study you must have referred constantly for the exam also. IS 456 for concrete, 875 for loads, 1343 for PSC, 1893 for earthquake design, resistant design, 1390 for ductile detail, SP16 design aids for 456, SP24 explanatory handbook for 456, SP34 concrete reinforcement and detailing, SP3370 for the design of water retaining structures. So these are a few ones. The structural designer can also prepare his own Excel sheet or design app in reducing the design effort. keeping all this information together. Present-day standard design softwares are capable of analyzing, design, detailing, and drafting structural details for a stated structural geometry, material specification, and load combination. So all that, you know how to provide the basic information graphically. You can describe the structure graphically by means of an CAD input and give it to the software. The software is capable of doing everything up to the drafting. If you specify the material specification and the load combination, you are going to get the final answers. So every engineer therefore tries to acquire the skill of using software and continuously go on using it to obtain the design outputs. Still, a first-hand experience of designing, at least in tables and handbook, is not calculating manually and using all the equations. For some time, it will go a long way in making design, get the feel of design, and it helps in checking the computer design outputs and other design drawings. The feel of the design is the most important thing. That comes from experience, from application, and once you are designing manually, it is what is normally explained as the finger or hand to the brain experience, which you are going to get, and it's going to be internalized within you, so that you have an understanding of the concrete behavior. Therefore, use the software judiciously. We consider just explaining before going with the behavior of an R.C.C framed structure. An R.C.C framed structure, its modes of action are basically explained under two major modes: action under gravity loads, action under lateral loads. The structure behaves like a multi-legged chair with the slabs as the seating planks, transferring the loads to the frame, the main beam, the secondary beam, and the columns. It's the vertical loads are acting in an R.C.C framed structure, it's just having many legs, and these structural components are rigidly connected to each other. So the beam bends and the column bends and try to take the load vertically, transferring it to the foundation. So the load specified and calculated based on the user's with the distribution are then stated for the gravity load to do it. So in this case, the moment is transferred from the beam to the column. The beams are loaded, the beam bends, and then there's a moment of resistance. This moment at the joint, when it turns, it also transfers the moment to the columns. And the moment is transferred to the beam to the column. This way, this. For the lateral load case, the load acting sidewise, and the building acts like a vertical cantilever, swaying sideways under these loads. So here, the loads are acting on the column, and bending occurs, and the moment occurs in the column, and the moment is transferred from the columns to the beams in this case. So these are two fundamental modes of action normally that we consider in understanding the behavior of the frame structure. If you consider land loads, main lateral loads is the wind load and the earthquake load, and we consider depending upon there are two classifications of the frame that we use, what are known as YMRF and SMRF, where the ordinary moment resisting frame is there and a special moment resisting frame there, where the special moment resisting frame, the joint details are specifically made to have a very good ductile behavior, and all the reinforcement details are done that way, and therefore we can allow a higher reduction factor in considering the effect of the earthquake when such provisions are made. And in OMRF, once these ductility provisions are not provided, we take a higher factor for considering the earthquake loads and getting the shear and the lateral loads transferred from the earthquake. But also, depending upon the nature of the region, we consider the intensity or the effect of the earthquake, and we considered loads to be the region to be divided into various zones. So we must have obtained this information about the loads and the region zone 2 to zone 5, and where you see how the loads are calculated. For zone 2, we just use what is known as the equivalent static load, and for zone 3 and 4, particularly 4 and 5, the dynamic considerations and response spectrum, the dynamic analysis become important. So these are basic actions, and fundamentally, if you consider the 2D, 3D framework, there are certain typical RC floor systems which are used. They're shown below. One is you have the frames which are regular straight two-dimensional frames with columns and beams and provided at regular intervals. And then the slab spans between these frames. And all these frames are connected by means of a cross beam. So the 3D integral action is there. But majority of the load taken by these main frame beams, and the slab transfers the load. The slab is acting like a one-way slab, and the loads are transferred equally to the 2D frames which are shown here. In case a larger column free space is required, sometimes it is the alternate column frame lines are avoided, and we try to provide main beams in the other direction, which are known as girders, and the frames are acting, are supported over the columns in one line and beam girder in the other line. And the load again can be transferred as a one-way slab action, or if the dimensions are small enough or comparable enough, you can have a slab transferring the load to all the beams, the girder and the beam, as a two-way slab system. In case you have a column location in such a way that it's almost squarely located and at equal distance, it's large for a slab to span as a one-way slab, then we can provide beams in two directions, and they are beams of equal weightage provided in both x and y directions, and the slab is spanning as a two-way slab in between them. Next comes flat slabs and flat plates, and when you try to avoid these beams in these lines and try to make the slab itself act as an element, and the slab is directly supported over the columns. In that case, the concentrated load coming on the column is quite high, therefore we thicken the concrete with the capital, and such a structure is called as a flat slab, because already have studied something about it. And this kind of columns directly, this is slab directly seated over the columns with the slab acting in both directions to a system without beams is commonly used for small rise structures, and similarly for apartment structures and structures like that, where even this capital not desired and these two spans are quite small when compared to the capacity of this slab, like 6 meters or 5.5 meters, where you can provide a square column plan. Then we do away with the capitals and try to provide a plate sitting over the columns directly, where the shear is taken care of by special provisions of giving a joint detail where the shear is taken care of by additional jointing mechanisms. Similarly, it is possible for us to extend this and provide the spacing between two systems is quite high. Then it is possible for us where it is high for the two-way slab also, like it can be a 9 meter by 9 meter or more than that. Then it is possible for us to make, and the loads are quite high also. The live loads are quite more. Then in such a case, you make it a series of reefs and some the slab. It still acts like a slab system, but it is a slab with a cross section with ribs very closely in between. It is sort of the grid floor. Then the effect of the grid floor is obtained by providing voids and by formers which are kept on the former, and then the ribs are automatically provided there, and they also act like the grid floor only. So just generally that way, therefore, the load path of the loads in the link is from slab to beam, beam to column, column to footing, and footing to the soil. The column transfers the load to the foundation, which in turn transfers it to the ground. We will now consider the design approach for the design of the elements of an R.C.C framed multi-story building. It's with a typical example, just to have some base. Considering a typical apartment structure, the design process starts with keeping the plan, and we locate the column positions and beam lines. We have to provide the column positions and beam lines so that it doesn't affect the function of the apartment. It doesn't come in between in the rooms. Most of the time it is in the wall lines, and the beams also go on the wall lines. And the dimension of the column also is so provided that functionally and structurally they are capable of taking the loads. So this column fitting is done first, so that all the requirements of the function, the utilization of the apartment is satisfied, and the beam lines also are laid so they are not appearing in the middle of the rooms, and we see a panel. Most of the time they converge with the wall. So this we provide the beam, and we consider the slab to act as one-way slab, and the dimensions of the slab are such that you have a short length in one direction, but a very long length in the other direction. You use it as a one-way slab, and you can make continuous one-way slab in directions where continuity is possible, or you can use it as a two-way slab when the two dimensions between the beams, the area between the beams is comparable, and we provide a simply supported or a continuous two-way slab system in such cases. This way, we arrange the slab beam column system. Once the column position and beam lines are acceptable, we first have to assume concrete sizes for columns, beams, and slab. So design is this process. We have to first assume the concrete sizes, and then check. We cannot start without a size. There must be a big size, and then by trial and error, we have to see that these sizes are okay, are acceptable, so that they can provide you an acceptable structure. To do this, to reduce the trial and error procedure, we use many thumb rules or basic heuristics, where the beginning sizes are going to be quite near the sizes required for design, and we have very few or small amount of iterations or changes to be made after checking after analysis. We see that, therefore, consider the preliminary sizing of the structural components. Mainly, in doing that, fixing up the sizes of the slabs and the beams, we use the serviceability considerations of deflection, which are more important to fix up and guaranteed. And based on that, we see that depths are such that the deflection is not going to occur, and we make sure about that, and then provide those basic sizes and go ahead with the analysis. In selection of these sizes, how do you do that? How do you do it for slabs, beams, and columns? Let's see. For the slabs, in Indian standard codes, if you take, you get the span to depth ratios, knowing the clear span, the effective span of the slab, it is possible for us to fix up the depth of the slab as on the span to depth ratio basis. We take the span to depth ratio, the lowest of 7, as 1/7 the span. It has to be that much, not less than that. And similarly, for a simply supported slab, it is 1/20th. For a continuous slab, it's 1/26th. So this L by D ratio of 7, 20, and 26 are starting points for the slab, the thickness of the slab. For here, these values are actually given for a basic span within 10 meters, and for I guess 250 grade steel, and for certain standard loads of 3 to 4 kilonewton per meter square. So these have to be modified for changes in span, changes in the reinforcement content, tension reinforcement, and compression reinforcement if they are provided, and the loading condition also, the load value, the live load value which is active. So these modifications are suggested for that using various graphs are given in the code, where it is possible for you to increase or decrease the span to depth ratios accordingly. Of course, all except for the 250 to 415 and 500, they have to provide higher span to the higher thicknesses than when compared to the Fe 215 steel, 250 steel, because to get the full action of the reinforcement of higher strength, we require larger depths. But the tension reinforcement and compression reinforcement reduce the deflection, therefore they have a contribution. And slab spanning in two directions, the shorter of the two spans should be used for calculating the span to effective ratio. But in Indian Standard Code, it is given for a slab span of up to 3.5 meters is the limit instead of 10 meters, and with mild steel reinforcement. And the ratio given is the span to overall depth ratio. And this is assumed to satisfy vertical deflection limits for loading class of 3 kilonewton. There are so many limitations there. Then you can assume a slab depth of L by D ratio of 35 for simply supported slabs and 40 continuous slabs. It's quite much when compared to the 7, 20, and 26. You see the two-way slab is so efficient that the load is distributed in both directions, that a reduction in slab depth is possible. Whereas, if you see, for example, in other like ACCE code, for solid one-way slabs, for beams or ribbed slabs, these values are changing, and these are given for certain span to depth. And two-way slabs, they give a coefficient which is a function of the boundary conditions and the span to depth Ly to Lx ratio. On the basis of that, you have a graph from which it is possible for us to obtain the thickness is starting from anywhere from L by D ratios of 40 to 45, and it is possible for us to provide a very suitable thickness that way and vary the thicknesses according to the boundary conditions. So the point is that the guidelines for slab thickness in IS 456 are being carried forward from previous versions without much change. So one can observe that one-way ratios are based on effective depth, two-way ratios are based on overall depth. The specifications are for 250 steel. And in today's practice, only 500 TMT steel is used and no other steel is used. And the two-way slab depth ratios are mentioned on the depth, slab to overall depth ratios, and they are not mentioned for different boundary conditions. One continuous, they mentioned that's all one category, L540. So it will be helpful to the design if changes are made to suit the present practice conditions. Present is best to assume the thickness equal to or near to the specified ones. Check for deflection after the section determination. This after analysis. Or you can use the ACCE code for guidance, but still, if you are not using the BIS code values, you have to check for the deflection and make sure the deflection is within the specified limits. If you consider next, go to the beams. There is a limitation, but anyway, in the slabs, it's also there that way. You may get various spans and various thicknesses. You will have to reduce the type of thicknesses of the slab in the same slab over the area to minimum 2 thickness values like that. You just cannot go on providing different thickness for different slab regions. For beams, the same L by D ratios are used, but you see that these limited L by D ratios of 2620 are not used in the case of beams for fixing the depth. They are the values below which the depth cannot go, because the deflection rates are certainly not going to be satisfied if they go below that. Therefore, based on the span and functional and constructional requirements, we normally fix the span to depth ratios for a span by 10 to the depth will be provided in the ratio of span by 10 to span by 15. A simply supported beam may have a span by 12 or span by 10 depth, whereas a continuous beam may have a depth of span by 15. And we use some in between values, and sometimes if the loads are lesser, you may go beyond span by 15. For columns, the orientation is placed deeper along the framing axis, and the widths are provided equal to the wall thickness in the other direction. Of course, for the beam, also one thickness provided equal to the wall thickness, and the depth of the beam is provided depending upon the span. Now, for example, if you take when I was designing, we were using the Reynolds handbook, and where you used values of load multiplication. You calculate the axial load coming in the structure. Depending upon the number of columns and the loads that is framing into the columns, you just design it for that load itself. Or if there is a one moment coming on this with a load coming from 3 directions, then you increase. If the topmost story, you have to consider 4.5 times the load and consider the capacity of the cross section to take that about 20. Similarly, if it is a corner one, when moment is coming from both directions and it's subjected to biaxial moment, you increase the topmost story dimension of column to 6 times the axial load and provide the cross section based on that. As you go down, as further the axial load increases, and therefore you can the capacity provision for lesser multiples of the axial load. This way, you can, of course, just consider the tributary area and take the load coming on the columns, and you can make a basic size assumption based on these observations or these calculations. Then we specify the material strength for concrete and steel after sizing. So the concrete slab size, beam thickness, column sizes are all selected. Then you provide what grade of steel and what grade of concrete we are going to use. Most often, as you know, today it's a unified market. All the steel mills produce Fe500, and Fe500 TMT bars are commonly used for all types of structures. We only vary the concrete grades, and the minimum grade of concrete has been fixed now as M20 for structural concretes. We use normally M20 to M25 concretes because the cost increase in the production of concrete M20 to M25 will not be in the same ratio of this 25 or 20, but only for a very small increase in cost, you can make an M20 concrete. That way, you can provide a lesser reinforcement of cross sections. Therefore, you take advantage of trying to use strength concretes in the range of M25 to M30 for beams and slabs, and you provide concrete. As you can see, that the compression member performance of the column performance is greatly enhanced by the use of higher strength concrete because it's a compression member and the capacity concrete very well is utilized. There also you can provide the section economy by using higher grade concretes like M40 or M35. Anywhere from 30 to 40 is commonly used. Of course, if the structure is going to be a high-rise structure with larger spans, depending upon the load conditions and the severity of the loading conditions, you still have scope to increase the concrete strength further to very high strength concretes also for special projects. You specify these things. You just make a, as you all know that how a computer program is done, and once you fix this, use the AutoCAD and feed in the inputs, review the coordinates, member dimensions, incidence, section properties, material class specifications, and section and joint restraint specifications. They will define the structure. Then you apply, consider the loads, calculate the self weight, consider the basic occupancy of the structure, and therefore fix the live load. You know the location of the structure, therefore, on basis from IS 875, you can pick the wind load in that location, and you can also know the zone, earthquake zone, which it is selected to, and take the earthquake load corresponding to that. And then you take, all of them will not be acting at the same time over the structure, as you know, and you must have heard about load combinations in lecture 3, session 3. So you know how, what load combinations you are going to take on the structure and apply them and obtain the forces. The bending moment diagram in the beams are shown, and the positive and negative moments are seen in the columns and beams, as you can see here. And it is possible for you to know at this stage to make a equilibrium and displacement check to make sure that these results are correct. Then you get the percentage of reinforcement after the design run is done in the program. For these moments that you obtained by analysis, it is possible for you to manually fix up the reinforcement percentage in the section and provide the percentage for the positive and negative moments at the various points, as you can see here. And these values of reinforcement percentages in the beams are shown here as the central section, left support section, right support section, like that for all the entire beams it is provided. And similarly, you have the reinforcement percentage for columns starting from the lower position of the column to the topmost point and reducing. Normally try to use the same section of the column with small variations in the concrete dimensions. Conventionally or more often, the concrete size is kept the same from the bottom to the top, and the reinforcement percentages are reduced as changed, and curtailment reduction in the diameter of the reinforcements are done so that you can obtain economy by changing the reinforcement in the upper floors. So you the design of the components now. We take the design of the slabs. The slabs are highly redundant surfaces which behave like plates, but we are designing them as a wide beam or a beam of 1 meter width. They resist the loads mainly as flexural elements that transfer the load beams. So you can have various types of slabs depending upon the boundary condition and the plan of the structure. You have one-way simply supported continuous slabs, and then two-way. If the two dimensions of the slab are comparable, you have two-way simply supported continuous slabs, and you have cantilever slabs where overhangs are provided. For manual designs of one-way and two-way slabs, moments can be obtained using the design moment tables of IS 456, and you see how we've just given a list of showing the moment diagrams and the load action of one-way slabs, how the load is transferred to the side beams, how the deflection occurs. Bending moment diagram there for the one-way slab. For the one-way continuous slabs, you see the maximum moment compared to the simply supported beam can be is reduced. The total moment is still the same, but some moment goes in the top sections and support portions are in tension, and it shares support sections also share the resistance and therefore have negative moments there, and load is transferred the same way as the one-way slabs, but moments are taken by the support points also. So for one-way continuous slabs for dead load and live load, you can get coefficients from the load and use the coefficient to multiply it by the load and then by the moments in the slab. Similarly, for two-way simply supported slabs, you can use the moment table and calculate the moments corresponding to the value of Ly and Lx and the Ly by Lx ratio. For simply supported slabs, you have table and for two-way continuous slabs, you have table for various boundary conditions where you see that the interior panels which are continuous in all directions are going to have the least moment 0.032, which is half of 0.064 for a simply supported one-way slab, and it goes on increasing to 0.056 for positive moment span on the four edges are discontinuous. And as Ly by X ratio increases, you can see that the Lx value increases and the Ly value decreases. The share of the load moment taken by the shorter direction increases. This is the basis. You can use these tables, cantilever moments that supports direct WL square by 2, you can use that value. So these values are picked from the table from the coefficients, you multiply the loads acting on it, and to calculate the reinforcement percentage required for those moments in the slabs by usual use of tables, or you can use your own spreadsheet for the calculation of reinforcement and provide that. So you see it's customary to provide a one-way slab. The main reinforcement in that direction is cranked at a distance of 0.1 L to take care of the possible negative moments which can come from the supports. And the reinforcement at the center is not required. You can crank up conveniently and use the same steel to take care of that. And the distribution steel is provided in that direction. Similarly, it is possible for us to provide the reinforcement for a simply supported two-way slab where the short direction steel is placed below and the long direction steel is placed above that, and bending up of the steel at the supports and cranking it up at 0.1 L is provided there also for the same reasons. And negative moment reinforcement is provided at the supports of a continuous slabs in both directions, as you can see here. The reinforcement is provided over at the top in the negative regions and the bottom in the positive moment regions, depending upon the values. But the reinforcement can be provided by cranking up the bars in the direction this way and but 0.1 L from the free support, and then the negative bar at the support section will have to be provided for a distance of 0.3 L and 0.25 L alternately. And you can provide this in two ways. One is the main bar can be bent up and provide that reinforcement alternately. Otherwise, you can provide a straight bar and a piece bar in the bottom here, and then a separate top bar is provided supported on chairs, whereas it is independent of the bottom reinforcement here. And similarly, you see that the 2S slab has corner reinforcement in the two-directional bending curls of the corners, creating torsion, and so they have to be held down to prevent curling up, which introduces torsional forces. So you provide corner reinforcement for us to take care of the torsional forces. So this is provided for a distance of L by 5 of the span, short span considered in both directions, and 60% of the reinforcement provided in the middle is provided there to take care of such curling up. So one thing is that when we provide a separate reinforcement at the bottom and top end, we may make it exclusively separate from each other. The raised space and the diameter of bars provided at the bottom here and at the top here are mutually independent. And as you see in a one-dimensional, the two-way continuous slab, the penultimate spans carry more positive moment, and the support, the last span carries more moment, and the penultimate support takes more negative moment, whereas the interior spans will take less moment. So it is possible for us to economize and provide carefully spaced reinforcement in such a way that we can save on the reinforcement by providing separate layers of reinforcement. In the case of cantilever slab, we provide the reinforcement at the top, it going into the, if it is, the slab is projecting outside, then we provide this is equal to LD at length. As you know all, that the moment is transferred from the concrete to the steel by means of bond. So to develop the force that is in the steel, you have to provide a development length. It is provided over length here. In case the slab is not going behind, then you provide a cantilever slab with a bend like this. So the anchorage is turned with a hooking up so that you can get the development length over this side this way, and then it will introduce torsion in the beam of course, but the way cantilever slab has to be provided with the reinforcement. So this is a typical arrangement, therefore, for the zone as it were considering the reinforcement is provided with the, so as I told you, the independent reinforcement data that we use in our office normally, as we provide negative bars with different spacings and at a distance of 0.3 L and the supports, and then bottom we only crank it up at the outer support, but no cranking at the middle, and we provide distribution reinforcement, and this reinforcement arrangement is done. For detailing and cutting the length, it's very important to note that the length of the rebar reinforcement bars is 12 meters. Then you will know the dimension of the span, how much cutting has to be done, what length has to be provided, that you carefully see that it satisfies the requirements of the detailing, and you provide them. And its advantages both two-way action and continuity in the structure here. But wherever continuity is available, if we provide that, whatever thickness you have provided is going to be the smallest possible, and the reinforcement is also because it's distributed between various support and span points. So there are very control specifications for the slab to act integrally as a composite member. You see that it's not something like a plain concrete member. it has to be confined within the reinforcement, and the confined concrete within the reinforcement will act and take care of the combined action, and also other forces of cage and the expansion are there, and they have to take care of that. So the minimum percentage of reinforcement of 0.15% and 0.12% are used for melt steel and high-end bars. And then we provide nominal covers to provide the durability requirements, and the cover changes from mild to moderate conditions. We go on changing the covers from a smaller value 20 to 75. The question of providing large covers like 75 and 50 are beyond the scope at this stage. We will see that later. So there is also a minimum spacing that they cannot be placed very close to each other. The maximum spacing also, as I told you about the intensity of the reinforced concrete action, the main dam steel cannot be further than 300 mm or 3D. Distribution steel cannot be further than 450 mm or 3D. We use those requirements. And ductile detailing like additional anchoring for slab bars, higher lap lengths, etc. can be adopted when the entire design follows special earthquake resistant provisions. You can have many point loads acting on the structure, and you may have non-rectangular spans like this also. For all these conditions, you can use yield line method for the calculation of the analysis, and use the yield line method to calculate for different boundary conditions like a trapezoidal slab or a triangular slab, and or a corner slab like that. And for varied boundary conditions like 3 edges supported, or supports with 2 edges but and a corner column, or a slab with a cutout or an opening, its advantage is for the designer to use strip method and design that. It is a very nice method of detailing and taking care of conditions. The slab also, to provide the reinforcement in positions, we use various types of cover blocks, chairs, and other things to keep them in position. We can use them, and hook the end bars to get the anchorages. These are all standard things. One word of caution in the case of slabs is that you have to take care of the formwork. Most slab failures are due to formwork failure. That is true, and therefore we have to take care of the formwork very seriously, and then check them and maintain them properly. Some important issues of concern in the case of slabs are that the cantilevers. The cantilevers are highly vulnerable components of structure. That if a failure occurs at the supported springing point, the structure is going to snap down, and therefore it is necessary to see that the top bars remain at the top and not provide unnecessarily long overhangs, because otherwise you have to satisfy the slab span to depth requirement. The dead load component increases and the creep wave increases, and you have to have pre-slab cantilevers spanning not more than 2 meters or 1.8 meters less. And then you have to see that the top bar stay at the top, and you have to consider a minimum point load at the free end for the cantilevers for accidental point load actions, and design that to make sure. Many designers prefer providing a boundary beam, stiffener beam all around to make sure of the unexpected loading conditions that the client may introduce at the end of the cantilevers. And in concrete slabs, we have to note that while concreting, the electrical lines are placed in such a way that they do not affect concrete continuity. Is a very important part of electrical line detailing or detailing. In the roof, if you provide fan boxes which have become potential leakage points, you have to take care of that. We go to the beams. The beams are rigidly connected to columns with the hugging moments at the support and sagging moment at the span. Because of smaller cross section, the beam section should resist considerable shear and also provide shear reinforcement. Various types of conditions, therefore, simply supported continuous cantilever beams. There will be main beams and secondary beams, and you know the action, therefore, of simply supported and the continuous or a fixed beam. where the load is distributed between the span and the support. And sometimes when the secondary beam transfers the load to the main beam, there can be a moment distribution and shear distribution like this, which you have to note carefully. And you design the sectional strength basis for flexure and shear. The design means the determination of the cross-section of concrete and steel to have a ductile flexural failure and providing shear reinforcement to resist shear and to have deflection and service loads within. So you have to satisfy both deflection and the strength criteria mainly. And you know the stress block parameter is just as written here for a single reinforced section. That's the steel yields first is a very famous strain diagram. This is the basis of the design and not this. The corresponding to the strain diagram, there is a stress diagram giving you the corresponding stress value and tension, and the stress block for concrete where majority of the concrete section have gone to the maximum compressive stresses obtained there, and the lever arm between the concrete and compression and tension will develop the bit of resistance. It is possible for us to have a doubly reinforced section also following the same principle of design. It is also possible in the case of beam to provide and make use of the integrity of the slab and beam and use them as L sections and T sections and use the the moment of inertia of the T section and the L section for calculation of deflection factors, and also use the areas that way where you can take advantage of the flanges as a part of the beam. In designing, one of the important factors that you have to note, very important thing we will have to run through, wherein we see these important points are the most important. In the diagram, as you see, the phase of the support, there will be, because of the steep gradient of the negative moment, there will be considerable reduction in the moment, and you can design the beam section corresponding to the moment phase of the support and not the center of the column. This factor has to be noted while designing the support moment sections. Similarly, the critical functions for shear is that the shear is considered at a distance d from the face of support, where the shear will be having a lesser value, and you can see that continuous beams and column beam junctions, you can design it for that value at a distance d from the face of the support. But in cases where a beam is suspended from the top, or when it is transferred over a point where the load is applied at the bottom here, or for brackets and corbels where the load is transferred here this way, these conditions you consider the face of the support only. Apart from this, as we have told that the minimum cracking moment has to be provided so that the concrete doesn't crack at low and create the suction failures before the utilization of the capacity of the section is completely done. So it should not be less than 0.85 BD by FI as the minimum tension reinforcement. Maximum tension reinforcement will be according to the placement consideration, so that it's 0.4% is taken as the limit, so that otherwise it will be cramming up the reinforcement there. So you also provide when the beam of the depth is more exceeds 750 mm, there's a depth of the rib, not beam, it's correctly here. Then you can provide side face reinforcement along two phases, let's say. So similarly, there are limitations for the maximum spacing of the shear reinforcement that shall not exceed 0.75 D. BSV by BSV is 0.4 by 0.87 FI is the minimum shear reinforcement to be provided. And we of course normally provide the shear reinforcement. That amount of shear is not taken by concrete. It's all known to you. So similarly, beams are to be designed for torsion, in which case majority of the torsion is taken by shear, increasing the shear reinforcement for a increased shear to be added to the ultimate shear 1.6 T by B, where the torsion to be provided. And in Indian standard in the highest code conditions, the beam is designed for a higher moment MT. It is M is equal to mu plus MT or mu minus MT, and provide higher longitudinal reinforcement. That is the basis for the torsion design. That is the beam predicted to torsion design. You take care of that by means of these formulae and design procedures. Where also the maximum spacing of reinforcement per data is given, and we cover to the reinforcement in case of beams are more than that of slabs from 20 to 75. Minimum 25 mm cover is always used, and the values of the minimum spacing between the bars are also provided because beam is a small cross section. You have to have sufficient space for the concrete to go in between and the vibrator to be introduced. That concrete can be deposited at the desired density, integrity of the structure, and the transfer of the load through bond from concrete to steel occurs. Therefore, you have to provide a spacing in such a way that concrete plays well, and maximum distance between bars are also specified so that they are not few and far between. It depends upon the reinforcement percentage. It is also given level 15. So, in a similar way as the slabs, we provide top bars and bottom bars are normally provided in layers. You can see only 50% of the reinforcement or 30% of the reinforcement can go from support to support. Whatever moment reinforcement that you have to provide at the center for positive moment, it can be corrected when you go near the source, and we can provide the negative reinforcement at the intermediate points at a distance of 0.3L or 0.25L, and only provide hanger bars for the shear for the to be suspended in between. In case you have a doubly reinforced section, it is necessary for avoid that reinforcement designed by the compression reinforcement percentage calculation that you provide. So this is the reinforcement data. You see that where 1L distance is the bottom bar is stopped here, and the top minimum 2 bars are provided at the top. That is also a precondition that you all know. So this is the minimum conditions, and in case of cantilever beams, if they are cantilevering out from the column directly, you have to provide sufficient development length by anchoring the rod deeply into the column. Otherwise, you have to take it within the beam here, so that it goes to a distance of development length in the span that way. So the development length concept is all well known to you, that we have to take care to get the necessary quantity of reinforcement. The code allows you to bundle the bars, but if you are bundling, you must have a reduction in increase in the development length depending upon the number of bars you are bundling. So the necessary bond effect is there, because when they are bundling, some phases of the reinforcement are lost and therefore will not be in contact with the concrete. So splicing, because the length of the reinforcement is limited, it is necessary for a continuous provision of the reinforcement. They have to be cut, and it is recommended that you have a lapping zone for the top bars in the middle and bottom bars near the support, not at the support. That way, the diagram is not correctly shown. Near the support, it should not go into the support region, and so the condition of reinforcement is not there. And you take care of the column beam junction correctly, so that the beam bars go out of the column bars and do not create a congestion problem. Again, one mistake here is that the outside, suppose this is the outside surface of the building and the beam is on the column, we normally try to provide the beam in the inside, going inside the column bars here, and this coming out here, because there will be slab here, and in slab there is sufficient cover available for the reinforcement, whereas here the cover will not be provided. You have to take care of some things in detailing in the column beam junction. So similarly, main beam, secondary beam junction, you provide hanger bars to take care of the secondary beam sitting on that. These kinds of bars are provided. In case you have a cut out for various sections like air conditioning, etc. It is common to have a cutout in the beams. Then you have to provide very closely spaced stirrups capable of sometimes take the shear in that region, and you have to put them at a very close distance and so that and provide top and bottom bars so that the increase in shear is resisted and the opening does not create make any reduction in the integrity of the beam. So there are minimum dimensioning considerations. Where minimum B by D is kept as 0.3 and maximum depth as 1/4 the clear span, because otherwise it acts like a deep beam. These considerations are also there for that. And in the case of ductile design considerations, we provide anchorages for top, bottom bars and provide sufficient anchorage lengths, and most important is that you provide very closely spaced shear throughout the length of the beam, so that the occasional, in the case of earthquake loads in higher zone 2, zone 3, zone, other things, where it is necessary to take care of the reversal of stresses, and so that therefore you provide the anchorage for the bottom bars also and provide closely spaced stirrups. Factors are very important in the case of ductile detailing when you are using them. In beams, you are asked many times by the client to provide a shutter beam, and you provide therefore wide beams of quarter depth. You have to be very careful in selecting that. In beam, people they provide considered beam to take that at some point. It is completely when the slab depth only is there, it is impossible for one to calculate and provide the reinforcement as a considered beam. It will not satisfy the deflection requirements also. You consider it that way, and it should not be encouraged. Such designs are not standard designs at all. When the length of the beam is long and the length of the rod is 12 meters, then normally splicing has to be done. It's normally done at one side of the support and one side of the near one support, and then there's staggered or split between this support and this support, so that all the bars are not spliced at one point. But these days, the industry has also geared up. You can order a special reinforcement for long beams and get the lengths more than 12 meters for such cases. Coming to the columns, columns are crucial components in a building. Safety and stability of the column depends upon the column strength. If the column fails, the building will certainly have stability, and therefore they are the main elements. Resisting lateral loads and lateral displacement should be kept to a small minimum to a satisfactory occupancy. So the important considerations in the column design are that the load transfer is eccentric, and therefore the minimum eccentricity has to be considered in providing calculating the strength capacity of the section. You have to make sure that the slenderness limits are such that it's a short column, and if there is a lack of straightness and other things may occur, therefore the moment magnification possibility must be there. And so you provide the reduction of column strength to such an extent we make the standard equation 0.4 FCKAC plus 0.67 FIASC, where you see only 5% of the concrete capacity and 67% of the steel capacity are considered in taking the strength to account for the eccentricity factors, and some minimum eccentricity is considered in the design. For columns subjected to moment and axial load together, as the axial load increases and the moment increases, the reinforcement percentage increases. You use the interaction charts and provide the reinforcement such that the maximum reinforcement percentage limits are also not crossed, and it is capable of taking the load and the moment at the same time. Similarly, for axial bending also make a trial and error procedure where the load factors that are used are PU by FCK BD and MU by FCK BD square, which are the two controlling facts which are on which the column strength and tension is dependent upon. So these charts use these basic parameters of axial load and moment, and you use the column interaction charts, or you can develop your own spreadsheets and calculate the strength of the column. So in this, normally you design it in such a way that the column is a short column, and it's also tried to make the column as a non-sway column by calculating the story shear is within this limit of sigma pu at hu, sigma pu delta u by hu hs, where it is the height of the story and the accumulated point to the loads acting at that level of the column. You take that and you see this value is this value you calculate. If it is less than 0.4, the column may be taken as a no sway column. If you take the condition in such a way that most of them are taken as made to be no sway columns, and to calculate the effective length and the so that you can always keep the effective length less than 1 in no sway columns. Otherwise, you have to use effective length factors more than 1 in case the sway conditions are crossed. So the effective length also is calculated on the basis of the bound conditions. Most often it is both ends really supported, supported, so that if the sway is there, you consider that, and the value varies from 0.65 to 2. Whether it's a completely cantilever-like thing where it is free to move, and the top is not rigidly connected to the column, it will be to the maximum. You see these boundary conditions and take the effective length of the column. And you see in the design of the column, you get a maximum moment, maximum and minimum moment only at the first story junction, and minimum load and maximum moment condition at the top. You consider these two considerations and provide the reinforcement the column. So anyway, the minimum of 0.8% of the cross-section area has to be provided to take care of the crack width control and the ductile action of the concrete. And for maximum of 6%, if you normally 6% only is the value of reinforcement that you use here, because it creates a lot of congestion in the concrete, and the beam column junctions will be difficult concrete. And we try to keep them below 4, even though 6% reinforcement is allowed in columns. If the column dimensions are quite big, where it is possible to facilitate 6% reinforcement provided. The minimum bar size, number of bars are also specified again for the same reason, that it is a leg and you have to take care of the legs. So any kind of accidental failure or bending or lack of straightness is going to create problems. You provide shears at closely spaced distances so that the main bar buckle in between the shear, and then therefore you have to see that almost every bar or every other bar is confined by means of stirrups and is held in position so that it cannot bend independently under compressive loads and buckle there as a reinforcement. And that will also confine the concrete inside within that with these confinement provisions. And it will take care of the action of the column as a integral confined concrete element. The nominal minimum cover of 40 mm is provided as the exposure conditions change. Also, the cover is changed. Similarly, in case of heavy reinforcement problems, where the you see, if you have spliced the column, you have to stagger the splices and provide them at in this fashion that there is no kinking, and these have to be staggered. If you put one at this point, the other one has to be provided at a higher level, not at the same point. And in case we use a very high diameter bars where this sizing of reinforcement is going to create congestions, you can use mechanical splices of various kinds and provide them. There also the mechanical places need not be used at the same point for the bars. So this kind of thing, the one important factor is that the dimension of the column and detail is selected that the column is strong and the beam can be relatively less stiff than the column. The weak, strong column, weak beam condition to resist the earthquake loads and lateral loads is considered. We normally say that the design strength of the column at each principal plane shall not be at least 1.4 times the combined design strength of all beams, shall be at least 1.4 times the design strength of all beams joining at the same plane. What important point you have to note ductile columns is that in soft stories where columns are not having walls by the side and freestanding columns are there, you have to use the minimum size of the column as something like 250 so that their individual action is resisted well by the columns and no accidental bending or failure will occur. And these days they have tried to provide retaining walls cast in along with the columns where they leave bars for the retaining walls and then cast the retaining walls later. Not allowed because the maximum strength required comes at the bottom portion of the column. It has been cast within the tight formwork, and you cannot use columns of 6-inch dimension and all that are used these days. They're all non-standard things which should not be encouraged. Most of the time, the base support condition are either you use a fixed support condition for hard soil and the hinged support condition for a soft soil so the moment is not transferred. Otherwise, you use a network of plinth beam and pedestal so that moments are not transferred to the footings. Footing design I won't concentrate much because you all have been introduced to that about say by the foundation details and they provide the reinforcement in such a way that the footings take the moment and from the point load it is better the cantilever and it takes the moment from that and it takes the moment at the support section and you take one way in the punching the column with the load try to punch through the footing and create a large amount of shear stress in the boundary around that region and you have to take care of the punching shear stress does not exceed maximum shear stress value. And it is the old style of providing tapered footings is not encouraged at all and use stepped footing which is presently because you have to cast the footing within formwork to get the maximum confinement of the reinforcement and provide the details selected. There are various types of staircases are used where you see that the stairs are independent of the design of total structure normally that way and you have different types of staircases like dog staircase, a car staircase and a L-shaped staircase and the spiral staircase etc. And a freestanding staircase is also commonly as a very special effect staircase and these days it is very common to have a sawtooth staircase where you don't have the slab there. So over time, certain standard types of stairs are there used, and you can use certain many handbooks provide very detailed design data. This is taken from Renault's handbook. They give you the design detail for calculating the design of a freestanding staircase, a sawtooth staircase, and a helical staircase. Curves are there. You can use them and design those staircases. It is possible to make use of the joint condition and consider common areas of flight of stairs, taking half the load from each flight and design the staircase. Stairs flights are all designed like inclined slabs, taking the load vertically down from the expected live load, dead load, and just design by a moment of WL square by 8 or whatever condition comes from these loading values as a simply supported condition you design. And you provide the reinforcement in such a way that the negative moments at the points of bending are taken care of by the detailing of the stairs here. Probably because of the positive time, I will not consider the design of water. So shall I go ahead with the to the end? Because water tanks are completely a different category of structures details where a good amount of information is required to know about the design part of it. You can, of course, refer to the material that I have given there and see some amount of information regarding the water tanks there. But I am of the main opinion that it is necessary to shift the focus of improving waterproofing specifications and financial provisions in the estimate for water tanks because it is impossible to, it is difficult to ensure good performance with the construction methods mainly due to like the way the tanks are constructed. You have to consider lifts and inevitable joints come in the walls. There are difficulty in working inspection for like tanks at with staging, and we have junctions with inlets and outlets and complexity of farm work is there, so that the crack width, the detail of the size of the crack is a function of construction and not a function of the design feature. That is the most important part there. It is impossible to contain crack widths by design as they are a function of construction. This is my important point. So that and no tension design needs highly uneconomical quantities of concrete and steel. So it is necessary for us to consider extreme good. These days chemicals have come with very high capabilities. You have to use those chemicals and provide waterproofing and protection of reinforcement and design the column for regular working stress loads, design the walls and the components of the water tanks for that condition so that the performance is guaranteed. Because it is constant contact with water, both minimum reinforcement percentages, number of phase reinforcements provided, spacing of reinforcements are more stringent than for ordinary structures. So these are the, except having the positive time, not covering the water tank in detail, I end the presentation with just an example of a project that we are doing. We are providing the framework for a Buddha statue in Karnataka. This, as far as we are concerned in structural engineering terms, it is an R.C.C. tower skeleton with some slabs, and it will be covered by the envelope of the statue body. The statue is the envelope going on it. We facilitate the construction of the statue with the cement and concrete ferro cement like specification that they use, for which the height of the statue is 113 feet, and we are trying to specify the good quality because it is a public structure exposed to rain and sun. It has to last for a long design life. We use higher covers, higher strength of concrete is used, higher strength of reinforcement with corrosion resistant reinforcement is specified, and is well analyzed in detail for earthquake and wind loads. You take care of all these other specifications very importantly for such structures like that, because statue is an exposed public monument which has to have a higher design life, and we take care of that by design provisions. So all said and done, the concrete and steel are denuding our planet. My Dr. Ajit Sabni's fellow professionals are active in advocating sustainable and green construction. If available, they will grab on a more sustainable material and stop the use of R.C.C. But at present, the alternative is not in sight. But even if we find one, the principles of design will be the same. Our knowledge will not be a waste. So I end the presentation with this and open the floor to questions.
Thank you very much, Yadunandan. That was a whirlwind trip for some of us back to our college days. We just went in and came out of the structures class. It was a good, refreshing course. Thank you very much for your presentation.
Thank you very much, sir. Thank
Now
you, sir.
I'll open up the floor for question and answers. One by one, you can unmute yourself and ask a question.
Yeah, sir. I am Manoj Chakraborty.
Yeah, Mr. Chakraborty, please go ahead.
Yeah, good evening. Good evening, also, sir.
Please.
Sir, the question one is coming, sir, the stability index. So, because we are doing the 3D model of analysis, so whether we need to check the stability index for finding out whether the column is sway or non-sway, or simply center to center column model, it will solve the purpose.
I didn't what the question did correctly. What I am telling is we try to provide the control the sway of the structure to some to an extent where it is possible for us to have more rigid columns use the sway effect and check the value within the columns so that they are not acting as slender columns. That is more useful. The slenderness reduces the capacity of the column to a large extent.
Okay, okay, sir.
Okay. Yeah, Dr. Krishnamurthy, you can unmute yourself.
Hello.
Please unmute yourself.
Yeah.
Yeah, go ahead.
Sir, I am Mr. Huddar.
Hello, Yadunandan.
Hello.
Sir, Namaste, sir. How are you, sir?
Dr. Krishnamurthy
Okay.
is going to ask a
Sir.
question.
Not a
Yes,
question,
sir.
but a very brief comment. Our relationship goes back decades, and I'm so proud to
Yes.
see. I think he once my student or whatever, but he has grown so much, and you enjoyed his over broad review of such a complicated subject in about an hour and so. Take care. God bless. I have many
Thank you
things
very
to
much,
say,
sir.
but I'm
Thank
sure
you.
there are others have questions. Okay.
Thank you,
I am
Dr.
very happy
Krishnamurthy.
Hello.
Happy
Hello,
to
sir.
see you also, and very glad to know that you attended this lecture.
Oh, I attend most of them. Ajit, and your group is so familiar to me. I'm trying to attend every one of them.
Thank you.
So it's good, sir. We also feel encouraged.
One series from N. Krishnamurthy, sir.
Yes, I'll be happy to do that. And I hope some of you attend mine.
Yes, sir. Thank you, sir.
Yeah, I
Hello.
think Mr. Huddar had a question.
Sir, I have got a question to Professor Yadunandan. Sir,
Yeah.
nowadays
Yes,
these
sir.
small apartment people, they keep one column width 150 mm. What is your comment on this?
Certainly, sir. That's what I put in my presentation. That 1 mm column, it will, from all theoretical considerations, it is not acceptable as the lateral load performance. Mainly, the minimum dimension of the column is given to see that the eccentricity is not there. If it's 6 inches, which is even with a small sway, the amount of out of condition eccentricity so much that certainly it will not take care of the behavior well in case of any movement of that kind. We have to be very cautious about such things. And these are all not people who are professionals like you will not do that.
That's what, many places always I oppose that. Many of the small builders, sir, you will get more space. Another 7 plus 7 centimeters extra will come.
I will tell you.
They forget the structural.
Okay. Okay. Thank you, Mr. Huddar. Next question,
I want to answer this question one line.
Yeah,
this
go ahead.
question, the minimum providing 6-inch thickness, I have given L-shaped and T-shaped columns with 6-inch dimensions to an apartment here, where the stiffness column is still taken off and the eccentricity effects are not there. If at all you're bound to use stiff columns, you can always use stiffer columns like that, giving stiff shapes of. If you take care of the molding of the columns in the shapes correctly using aluminum formwork and things like that, it is possible to provide 6 inches. Otherwise, not acceptable professionally.
Thank you, sir.
Yes.
Okay. Next question, please.
Sir, can I ask a question?
Yeah,
Can I
who's
ask?
this?
Sure, sir.
Yeah, sure.
Vijayendra. Hello, Vijayendra sir here.
Yeah, go ahead. Yeah, Vijayendra, go ahead.
Namaskar. Edu sir, namaskar. Sir, I have two questions on plinth beam. I have two questions on plinth beam. One is, when you call a beam as a plinth beam, that is, what is the distance, maximum distance from the pedestal to the plinth beam level? Like that, the in-between column length is how it is designed. Is it for, or is it considered in the design? The distance between the pedestal and the plinth. The second question is, when you're designing the plinth beam, usually what I see is they provide the bed concrete below the plinth beam and they design it. But is it considered, is the bending of the plinth beam is going to introduce the reversal of the moment on the column because of the elastic support? The soil yields or response or provide a flexible support to the beam. Is that considered in the design in calculating the moment transferred to the column from the plinth beam?
It all depends upon kind of vertical that you are transferring to the plinth beam. If you are not providing only the wall load part of it, actually the tie effect which comes from the horizontal reaction at the support of the column is going to reduce the bending effect there, where the plinth beam mainly is a tie element most of the time, and the amount of moment that is due to the vertical load is only a one-story high masonry with all openings, normally will not be much. And it will not be a very serious consideration to take those moments effect, because it's not it's effective as far as the frame is considered, is tying the concrete columns together.
Okay, thank you, sir.
Sir,
Thank you, Vijayendra.
Sir, good evening, sir.
Who's this?
Sir, I'm Deepak, sir. I'm Deepak.
Yeah, Deepak, please go ahead.
Sir, I'm Deepak, sir. Sir, Yadunathan, sir.
Yes, sir. Hello, Deepak, sir.
Sir,
How are you?
Fine, sir. Sir, how are you, sir? Sir, 6 inches.
Very fine, sir.
Very. If the span is less, why can't we go for 6 inches? Cumulative, if we take it, the structure, its stiffness
It is not a question of the span, Deepak.
Yeah.
It's not a question of the span. It is a question of the height. Number one, and the eccentricity that it can cause due to any accidental or any unintended change in the tightness of the column. How well are you going to maintain the structure? That is the main thing.
Okay.
That is why we are not allowing that. That's the main thing.
And one more thing, sir. For an earthquake design, the tie beams, why can't we have a diagonal ties? Is there any this thing, sir? Usually we connect the columns in the X and Y directions. Hello?
Maybe you can try. You can try that.
Hello?
You can try that. No, you can do it. Hello. Practically, because of the openings and other things that could come in the building, it is not possible in where people are using it. That's all. Functionally, if at all it's not a problem like in the steel structures, you can provide braces and diagonal ties to resist lateral. Certainly, you can do it.
Okay.
How you cast it, how do you detail that are all a problem. Theoretically, it is possible.
Okay, sir. Thank you so much, sir. Thank you, sir.
Okay, thank you, Deepak.
Thank you, sir. Thank you.
Question, please.
Sir, good evening. I would like to have a clarification.
Hi, Dr. Naikar.
Yeah. So, sir, you made a mention in order to achieve economy, we have to do more with less material. Okay. So, by
Achieve
means
economy?
of better, in order to achieve economy, we have to do more with less materials.
Yes.
Okay. So, by means of better modeling and better materials. So, metal we understand when we use high grade concrete, high grade steel, that's understandable. So, can you please elaborate on what do you mean by better modeling?
That means it's stress situation that you're creating and writing the equation for writing the stress block and the strain as it appears there in the cross section, in the beam. If you take a correct assessment of how things are developing by laboratory experimentation and all that, see this model itself, like for example, if you take the linear stress strain equation that we are using for working stress, this model is considering the collapse model, which is a better model of the behavior of the structure than the working stress minimum permissible stress model. That is economical now. Otherwise, it wouldn't have been. You are utilizing the capacity of the structure to a larger extent.
Okay. Okay. Thank you, sir. I have got another. I need another clarification. In case of footing, so it is always economical to go in for a stepped footing. But when it comes to construction, there are challenges. So can you please elaborate how to go about it? Stepped footing. It cannot be cast at a time. So it will be cast in two stages.
Yes.
So can you please enlighten on that?
It cannot be cast at a time. Yes.
So if there is a gap of say more than 2 to 3 days,
column cannot be cast at a time. You column continue with the vertical joints like that.
No, sir. I'm not talking about the columns, sir. Stepped footing.
No. As you found out that the integrity of the structure, the one thing is it cannot, you do a column first stage at the bottom thickness in one time and the top portion 3 or 4 later. Better do it the same day, waiting for some time. That's all. Over that, as soon as the column is complete, bottom stage concreting is complete, immediately put the shear for the top portion. And
so
that amount of gap is
probably,
okay.
Yeah, two days gap is all right, sir.
I don't think so. Yeah, maximum 1 day. Or immediate is the best thing. Taking an 4 2 or 3 hour gap is good.
Correct, but there will always be tendency outside people will delay a day.
Our fundamental principle is that concrete will be cast within forms and it will be best. That's the best.
Yeah, but obviously there is a difference between column and casting.
In a slope footing, you can't provide that.
Yes, yes. No, in case of column and casting, if even there is a gap, there is always rebars available. That will not be very serious. But in case of columns, there won't be any reinforcement between two castings. So there is a main issue. People delay more than 2 days or 3 days sometimes. Immediate is good, but
maybe possibly you can provide some connectors, shear connectors to the top and bottom and provide.
Yeah, we do that, sir. We do, but that quantity sometimes become quite significant. That's why I'm asking. Thank you so much.
There issues.
Thank you so much.
So
Thank you, Dr.
You're asking questions in such a way that you know everything about it. You can do that.
No, sir. We do. Sometimes the client will question, so that quantity will be too much and all that. So we would like to manage without shear connectors.
Okay.
You are asking.
Thank you, Dr. Naikar. Now I encourage some students to come forward and ask questions if there are any. Any students would like to ask questions?
Hello, sir.
Yes.
Myself, Raghu, sir.
Yeah, Raghu, go ahead.
Yadunandan, sir. Namaste, sir.
Yes, sir.
Sir, in one of the slide, you shown that caps model. The upper floor is having higher percentage.
Yeah.
Hello, sir. Am I audible?
Higher percentage?
Please be little louder.
More in upper floor compared to the lower floors. In one, we'll get this type of percentage of steel, sir.
Yeah. You may get more percentage
You
of
shown one.
reinforcement at the top.
What's the question?
More
Yes, sir.
percentage of reinforcement at the top, less percentage of reinforcement at the bottom
No,
section.
sir. Higher percentage of steel top and lower percentage of steel in lower floor.
Bottom. But you
Bottom
see,
floor. You shown in
so
one
you
of the
decide.
slides.
As for yes, you are you asked a good question. You see, the top section where the reinforcement percentage is high is a local region where the reinforcement is asking more reinforcement. You can provide it there, and you can provide a normal requirement is reinforcement is there at the bottom. That reinforcement need not have to come right from the bottom.
Okay.
You can provide more reinforcement at the top and less reinforcement at the bottom. Instead of curtailing and reducing the reinforcement, you add reinforcement at the top. It is as much permissible as far as I am concerned. That is the answer.
Okay, sir.
Because the section analysis is for that section, that region. That region demands more reinforcement. You provide it there.
Okay. But in general,
that was a good question. That was a good question. It's a big doubt people have. And because the reinforcement requirement is high at the top, they start providing that reinforcement right from the bottom. Maybe many other
Thank you.
professionals
I think we are coming to the end of the session.
Answer that way. Yes.
Yadunandan, I think we are coming to the end of the session. I'll allow one question, one last question for the day.
Yes, sir.
Anybody wants to ask a question?
phone voice
Umashankar? Is this Umashankar who wants to ask a question? We can't hear you.
No, he's muted.
No, he's not muted.
It's okay. I think we lost him. We can go to the other. If there is anybody else.
Anyone else? One last question, please.
Hello.
Yeah.
Hello.
Suhas.
Yeah, Suhas Rao. Please go ahead.
Yeah.
Sir, when we consider base year for earthquake loading, actually we will get high base year at the bottom column, right?
Yeah.
Yeah, but while we designing in the world, we can see column of same length from bottom to top. So what is your comment?
Same length.
No. With from base, due to the base year, it will bottom column will be having more base year. So we have to resist that.
Yes.
So that's why we have to provide a little bigger dimension when we compare to the top columns. If
that dimension thing depends. You can provide the same dimension, but reinforcement will change.
Yeah, but if it is for earthquake,
you have to take care of the shear. Shear is resisted both by the concrete and steel.
So you are saying it will be resisted with the same length, same dimension.
You can, of course. I don't say it will be resisted. You have to find out the section requirement. It is what you are telling is correct. It is more, and you have to provide a section to resist that. But it doesn't necessarily mean that you have to put bigger concrete section exactly. Sometimes if you have a very high multi-story structure and you don't have shear walls and other things to interact, it is possible that you may need a larger concrete section with a restraint of the maximum percentage of reinforcement. You may have to provide thicker columns. You may have to. That depends on the situation.
So by providing a little increased percentage of reinforcement, we can also try. That's what you're saying.
Yes, you calculate. You know the base shear value. You calculate the shear and then find out how much of section is required. You can always do that.
Okay, sir. Okay, thank you.
Okay, thank you.
Sir, good evening, sir. I have one question, sir.
Who's this?
Yes, sir.
Sir, Praveen Nigam. Sir, I am designing one hall of size 11 meter by 15 meter. For where I need to give a beam size of 500 by 800, but it is not pass in grade of concrete M25. can I increase the grade of concrete for beam, but not for column? Column is still passing in M25. Can I increase the grade of beam only?
Yes, you can do that. Provided the beam column junction, how you take that, you do that, it is possible. Yes, you can do it.
Then in that case, then how?
One thing, the reinforcement calculation that you do beam column junction for the negative moment that is coming there, you consider the column strength, the concrete strength, and do it better. That's all.
For the negative moment testing only.
Yeah, negative moment at the outer wherever columns are coming, because it's a big hall. With the moment, end moments, maybe that way there. If you're using, I think it will be certainly possible.
Sir, what I am.
You can use higher grade of. See, if you can use a higher grade of concrete for and lesser grade for beams, the other way is also possible, but you have to take care of the big column junction. That's all.
Okay, sir, I am giving higher depth beam in one direction and lower size beam in other direction. That is okay, or I need to give beam depth equal in both the direction? Which solution is better, sir?
The shorter direction beam you have to take the deeper one. Yes.
Yes, sir.
Okay.
Yes, sir.
Okay, thank you.
Sir.
Thank you,
sir. Thank you.
for that. Professor Yadunandan, that was a wonderful presentation what we had today. We greatly appreciate your time and the way you have presented. And all of the participants have enjoyed this particular lecture. And thank you very much for this class. And
sorry,
I
only one thing
all
that I have to.
Yeah, please go ahead.
Hello, sir.
You have to excuse me because in spite of the trial run, I could not take the water retaining structures in detail because it was quite a chapter, and even in the trial run, it came to sit and up and spoke so many other things in between. I had to put that down.
Yeah, we appreciate that.
I'm sure. Can see.
We have other occasions when we can definitely accommodate these lectures, Dr. Yadunandan, and we'll be very happy to have you back amongst us. And friends, one more request, what I'll be making once again, as I mentioned at the beginning, please register yourself for the series so that we can reach you, because we will not have your contact details if you do not register with us. And the association would definitely like to interact with each one of the participants. Kindly register if you're not already registered. With this, I think we'll be ending today's lecture. And I thank everyone for participating in this particular lecture. Thank you all. Have a good evening and a good weekend.
Thank you very much.
Good evening, sir. Thank you.
Yeah, thank you so much. You really took us back into the classroom. It was,
we enjoyed.
Compacted. You have just initiated, so we want you to have now exclusive session on each topic.
Yeah.
Okay, sir. Yeah, thank you very much. Yeah.
With this, we'll end today's meeting. Thank you.
Welcome. Very happy to interact with you.